Hello everyone. I'm going to do an overview. Oh, first of all, my name is Féidhlim Harty. I run a company called FH Wetland Systems Limited, a small environmental consultancy unit based in Clare. And what I'll be looking at today is natural treatment options for treating wastewater, so domestic scale or municipal scale, and just other applications then for reed bed systems and wetlands for use as buffer zones and that type of stuff. So I'll jump right in. This is my first slide, because this for years was my first slide and it's not as pretty. So this is a septic tank outfall from a municipal system in East Cork. Very, very common all around the country, still too common, to have this type of thing still active, just flowing straight out from septic tanks into receiving waters. And this is the stream beside that septic tank. So you can see that the sludge there has been coming in for years and building up and accumulating in it. What I want to do first is talk very briefly about why wastewater is an issue. So essentially what you can see here, the suspended solids loads obviously are through the roof. And the most immediate problem with suspended solids is simply just clogging up spawning beds, making it difficult for fish to see food, and just reducing the overall habitat value within the stream. So that's a very important one. But ancillary to that then, you can see the slightly greenish colour of the algae. So that green would be the result of nitrate and phosphate enrichment. And then when you get warm weather and sunshine coming in, the algae will grow and generally it's a sign of eutrophication, nutrient enrichment within the water. So there are a number of issues. The other is BOD, the biochemical oxygen demand within the water. And that's basically a measure of the food value that's in the water. So the higher the BOD, the more the microbes can have a party, basically, and feed on it. Now, if you overfeed the microbes, they'll breathe too much oxygen, they'll take in oxygen and strip it from the water. So that was the reason for the fish kills in the late 1980s, when there was silage effluent and the like getting into watercourses around the country. That literally, it was just stripping the oxygen out of the water and fish were drowning. That was the cause. And still, BOD from yard runoff, from silage ponds, whether it's clean yard runoff or dirty yard runoff or slurry, any of that gets into waterways raises the BOD in the watercourse. And as I say, when you get into the sea, the phosphorus won't be a limiting factor, but nitrogen will. So nitrogen from sewage or from industry or from agriculture will all contribute to the general levels of enrichment within the sea. And you can see the green algae there growing on the water in Cork Harbour. That's the result then. So nitrates, phosphates, microbial pollution, so pathogens, that's another issue. BOD, suspended solids, those are all issues. Another thing to bear in mind with water is just hydrocarbons and general stormwater pollution coming in from roads. You can see here an oil spill on a small back road. And so those are the main pollution inputs that we have around the country. But there's another factor in the wider landscape to consider. This is an old photograph of a boggy corner of a field in East Cork, close to where I grew up. And that was drained and turned into housing. And when you take out the boggy fields and the bogs and even wooded corners, when you take those out of your landscape, what ends up happening is that in dry weather, your streams dry up completely. And in wet weather, you can suffer from very bad flooding then, just due to the changes in the landscape without ever factoring climate change into the whole equation. So those are some of the challenges that face water and waterways. And we can see if we look over the last 30 years, from the early 1990s up to nearly the present day, you can see here that the number of seriously polluted rivers has dropped from 91 down to 2 rivers recently. So that's a huge drop in the number of very seriously polluted rivers. But one of the slightly worrying trends that goes in parallel with that is that from over 600 odd high quality rivers, we've had a drop down to 355. So that's nearly a 50% drop in the number of high quality rivers around the country in the same time period. So that's quite a worrying thing. It's obviously not a trend that we want to be encouraging. But if we look at those high quality rivers a little bit more closely, there's a more worrying trend. High quality and reference conditions, so that's kind of pristine waterways, have dropped from 13.4% of all of those waterways down to less than 1 in the 2013 to 2015, and they've risen again slightly to 1.1. But there's a huge drop. To have 1.1% of all of our rivers and streams a reference quality is very, very poor. So all of those inputs that I mentioned, whether it's coming from farmyards or domestic septic tanks or municipal systems, those are all having a direct impact on the quality of our waterways around the country. So it's a very serious issue that really, I suppose, needs to be grappled with, isn't really being looked at terribly closely. But things are changing, but they're changing kind of slowly for something so serious. So how do we begin to look at that? Well, we can get clues from looking at natural environments. This is a stream habitat that we widened out into a buffer zone in East Cork, probably about 25 years ago. You can see the old stream channel here along the boundary, grand and straight, and we pulled out the area, planted it with various different wetland plants, and you can see this is 2 years on. There's a silt area after accumulating here, so that gives us an immediate clue that the silt settles as soon as we create a space where the water can slow down a bit. And similarly, you can see there, this is a constructed wetland in Wexford. There's wetland plants at the edge of a pond, and the floating scum in the pond has accumulated at this sewage treatment wetland. It's accumulated where it's been stuck by the plants. So the plants act as a physical barrier to filter the scum that forms. Similarly, in a factory in the Midlands, this is a newly planted wetland, and you can see the green of the colour here where the algae is growing as a result of the sunlight and the warmth. And the algae is growing, but then once the algae grows, it begins to get filtered out by the plants themselves. And those plants will thicken up more, filtering out this surface scum that's floating. And you can see very quickly how you begin to get a lot of the mechanisms that are also active in conventional sewage treatment. Your filtration, your settlement, and nutrient uptake of various forms. And even in the winter months, the constructed wetland can still function. The wetland plants growing on the surface fall into the water body, and basically it acts as a large horizontal flow fixed film filter. So you've got your fixed film media, which is your leaf litter and your plant debris, and then the bacteria build up around those as your microbial scum layer. And as the water moves along through the wetland, it's those microbes actually that do a lot of the work. So what we're doing really with constructed wetlands and reed beds is building a large creche for bacteria, essentially. So we want those bacteria that party so hard on their BOD loading, we want them to really proliferate within the wetland so that by the time the liquid gets to the far end, the bacteria have done their work, and then the water can go back into the receiving environment safely. So if we look at how do we engineer a natural landscape to form a constructed wetland, taking those elements into account. Here's a system in North County Dublin. So it's fully plastic lined. There's a plastic liner underneath that. There's about a foot of soil put back in on the plastic liner. The bed of the soil is made level, planted up with various wetland plants. There's 2 inlet pipes, one here and one just out of the frame, and the liquid moves across the surface of the water and gathers in an outlet pipe at the far end and off on into a percolation area. So what we've done is we've taken the natural treatment mechanisms and we've maximised their potential for treating the water within the wetland basin. This is the planted water depth. Full operating depth will be about 4 inches. So it'll be a bit deeper than that, maybe 4 inches deeper than what you see there. So that when when the plants become established, it'll provide that volume of water. So there's a residence time within the basin as well as everything else. And one of the important reasons for the residence time is if we have a 10-day retention time within our basin, it gives us time for uptake of or removal and die-off of enteric bacteria. So enteric, as the name suggests, are inside. Those bacteria from inside our own gut are particularly fond of the temperature in the gut. As soon as they leave the body, they begin to die off. So a 10-day retention time will give you a good die-off of those bacteria before the percolation area. So that's what's termed a soil-based constructed wetland system. We've got our inlet pipe, our water level is sitting above the level of the soil, and we've got our outlet pipe collecting at the far end and off to the next stage of treatment. So there's 3 main types of wetland. There's the soil-based constructed wetland, horizontal flow gravel reed beds, and vertical flow gravel reed beds. And I'll look at the others in a few moments. If you don't need a plastic liner, you can be a bit more imaginative about the shape of your system. So this is another system in East Cork on a clay liner. There's one inlet pipe just there and another inlet pipe beside it there, and then it flows through the basin and gathers in a perforated pipe at the far end, and again onto percolation. And the reason why we could play with the shape a bit more was because we weren't restricted by liner efficiency, really. I suppose if I buy large rectangle of liner, I want to get as much treatment space out of it as possible. Whereas in this case, we didn't need to because of the heavy soil underneath it. Here's a municipal system in North Cork, just north of Cork City. This is on the day of planting. And here we have the same system about a year later. So you can see how the wetland plants get established quite quickly and begin to form a viable filter very shortly after planting. The flow control is controlled by a very simple weir. We've got our wetland is connected to this outlet pipe here, and there's an elbow on the pipe which allows us to control the flow very, very easily. If we rise that pipe up fully, up into an upright position, it holds the water in the wetland. If we drop it down, it means that we can plant the system in relatively dry conditions, and then we bring it up to about 4 inches height for operating depth, and that controls the level right across the system. That's particularly useful for domestic systems, so when you go on holiday, your system just stays moist. And then as soon as you start flushing toilets, water starts flowing out here at the far end again. So looking at the gravel reed bed system, we've got our inlet, and our liquid is about 2 inches below the surface of the gravel. And so the active site is underneath the gravel surface, around the root zone of those plants. The liquid will flow out the far end and onto percolation again. So we've got our settlement, our reed bed, and our percolation. So it's essentially, the settlement and the reed bed is essentially taking the place of a standard mechanical sewage treatment system. So it's providing us with secondary treatment. We can always go for tertiary treatment as well if we so choose, and that just means making the system a bit bigger or having another system after that, usually a second system following that one. Here's a gravel reed bed system in North Cork, and you can see here just the planting within the gravel, and the water surface is literally just below the surface of the gravel. Something to watch if you're designing or building these is to make sure that the gravel is level. On this side, I think when we arrived, the gravel was about 4 inches higher at the top left than it was on the bottom right. And the risks there are that these plants will dry out, and the lower plants will, the water will break the surface of the soil and just become a potential pathogen risk within the garden. So getting the levels right is important before the day of planting. So what we did there is we just got a couple of shovels and rakes and leveled it out before we started the planting itself. This is a similar system design in County Clare, and you can see how the common reed has just taken over the whole system completely. It's really pushed up. That's probably 2-3 years into the system. So the vertical flow reed bed has a pumped inlet, and it spreads the effluent across the surface of the media. Now, sand is what's recommended in the EPA Code of Practice. My experience with sand is that it's actually very difficult to get the right grade of sand. I think there's one quarry in Wexford that might have it. And what I prefer is a quarry grit, just a clean quarry grit, so that the liquid can spread across the surface and soak down into the media. And then there's progressively larger grades of media as you go down through the system. That gathers in a 4-inch pipe at the base and on to the next stage of treatment. So the plants that are used, the common reed is the one that's most commonly used in the vertical flow and horizontal flow reed bed systems. And then all of them are actually used in the soil-based constructed wetlands. So soil-based wetlands have a greater diversity of plants than gravel reed beds. This is a particularly deep-rooted plant, so it's particularly good for the gravel systems. Whereas in the soil-based wetland, it's actually the leaf litter at the top surface that provides the active site for bacteria to stick to. So we're just looking for material that will grow well, decay into the basin, and then provide that mat of leaf litter at the end of the season. So common reed, bulrush, yellow flag iris, and a number of others. Branched buried is another common one that I'd use. And then if you want a little bit of variety for establishment phase, watermint is very good, fool's cress, watercress. Those are all very good plants for getting a good flush of material nice and early on in a soil-based constructed wetland. So that's the wetlands covered in a nutshell. I want to talk very briefly then about other systems that are very much related, but slightly different. So briefly, you're all probably very familiar with this graph. Okay, our carbon dioxide levels in the atmosphere are too high. We need to get them back to safe levels, or we're pretty much snookered. And we're already seeing the results of that snookered. This is the storm damage in Lahinch, flooding in Ennis. That's more storm damage in West Clare, and again flooding through the River Fergus in Ennistown. So it's not a million miles away. Do you know, I'm living and working in Ennis now. This is home turf. We're seeing the effects of climate change right on our doorsteps. So what does that have to do with sewage treatment? How is that relevant? Well, if we use a mechanical sewage treatment system for our sewage treatment, we've got an ongoing electricity input in order to keep that system running. So our carbon dioxide output per year, this is from EPA figures and from research that's been done by Lawrence Gill and Donata Dubber. So our carbon dioxide kilograms per year, about 177 kilograms per year for a very efficient mechanical system, up to about 750 odd for the more energy intensive units. Now, if we've got a media filter system like a coconut filter or peat or a sand filter, something like that, the pump only kicks in when there's liquid there to be pumped. So it's a much lower input. But constructed wetlands, gravel reed bed systems, percolation areas, they're all pretty much electricity neutral as long as they can use gravity. But then we look at the zero discharge willow systems, zero discharge willow facilities, and your average zero discharge willow facility will actually mop up as much carbon in the willow biomass as an average mechanical unit would spit out. So personally, what I'd love to see is a willow plantation of some sort on every site in the country where there's space to have it. So you get uptake of your nitrates, uptake of your phosphates, uptake of a lot of the liquid, and you also get sequestration of atmospheric carbon. So as a way to deal with climate change, it's a very good way to tie in climate sequestration, carbon sequestration measures with the sewage treatment process. So this is a diagram of your standard lined zero discharge willow system from Denmark. We've got a pumped feed, which rises up over a spreading media system, and that all sits on a sand layer. The liquid soaks into the soil, and the willows take up the liquid then over the course of the year. And just very briefly, I'll go through some of the construction photographs. This is a project that we worked on in Limerick. We excavate our ground. That's heavy clay underlying peat, so there's very little soakage, and that was the reason why the willow system was wanted. So we have a protective membrane that goes on the ground. The plastic liner sits on top of that. That gets covered with another protective membrane. And then there's pipework at the base as a drainage layer. Sand goes over that. On top of that sand layer, we put a layer of soil to about a metre depth or so. And then we put another sand layer on top of that. There's a spreading block. It's like oyster netting that's curled up into tubes. Essentially what these are rigid modular units that provide a very high void space, so with very little weight. So a gravel trench would have a tendency to sink and to compress the soil. So here we lay those modular units out along the top surface of the sand, and then to finish we cover the whole thing with a geotextile membrane to protect it, and then cover it over with soil. That's covered with a plastic layer and then planted with willow cuttings. And what you're looking at is the foreground, not the background. It's just the foreground is positioned in a wooded setting. That's a Danish system there. This is the system in Limerick 2 years later. So you can see how those trees have grown on that site. Willow trees, as luck would have it, have about the same requirements for nitrates and phosphates as humans have in terms of nitrate and phosphate output in sewage. So you put it down to luck, or you could put it down to millions of years of evolution. Take your pick. So the coppicing regime that's used is that you'd strip one side of the basin, so 3 rows on one side, and you'd cut them all back on a given year. And then on an alternate year, you'd strip down the 3 rows on the other side. So what we can see here in the foreground is fresh growth. The photograph was taken in June. They would have been coppiced the previous February. So that's 3 months growth, 3, 4, 5 months growth. So there's a lot of growth coming back. That's about 1.5 meters to 2 meters high already. And then in the background, that's willow that's coming into its 3rd season. And then at the end of the season, they'll be cut back. Now, something that's more cost effective and, to my mind, a lower resource input is the Danish design guidance for unlined willow basins. And it's basically the same general idea. You've got 2 spreading lines rather than 1, and then your willows are spread out in a bunded basin, but there's no liner underneath the base. And Denmark generally has very sandy soils, and this is one of the methods that they use to just to mop up nitrates and phosphates en route into the groundwater through those sandy soils. And it's important that if you use willow systems as part of a percolation area, that you modify your percolation piping before you do so. This drawing is based on the EPA Code of Practice, but it shows a modified pipe layout. So if you're familiar with figure 7.1 in the old EPA code, it had 4-inch pipes in the cross section, and what we've got here is a 1-foot pipe cut in half with a geotextile membrane over it, just to widen us out to a 500mm trench width, and then you're away from there. And there's a very, very effective splitter unit that's available in County Sligo, rivet splitters, and that provides an excellent gravity distribution. So you could have up to 12 outlet points going to different parts of your willow basin in order to make sure that you don't overfeed the near end and then end up at the far end being deprived of nutrients or deprived of liquid. Depending on your composting regime, then you can grow your willows slightly larger if you want to get firewood out of it. So this is 3-year-old willow growth in Denmark, and you can see the size of those logs already. And if you grow that for 4 years, 5 years, you just end up with a bigger log for firewood if that's something that you want out of it as a viable crop. And if you use that firewood to offset fossil fuel purchases, then your carbon sequestration can be very effective in terms of offsetting purchases of fossil fuel carbon. So I want to look very briefly, if I can get the slide to open, at the standard interactions between sewage treatment and agriculture, because basically as land mammals, we have an interaction with our environment. So that kind of goes without saying. But at the moment, what we tend to do is we tend to consume the fruits of the land and then flush them into a toilet, and they end up going into the rivers, into the sea ultimately, after a lot of treatment. So is there a way to change that? So we've got energy mainly from fossil fuels. So there's energy, huge amounts of energy go into manufacturing nitrogen fertilizer in particular. A lot of energy goes into agriculture, and there's a certain amount of energy then goes into standard treatment processes. So in the form of natural gas, in the form of diesel, and in the form of electricity. So there's a lot of energy that goes into all of those processes at the moment. From agriculture then, inevitably, we get feces and urine. You might have thought that food was the natural product of agriculture, but make no mistake, ultimately it's feces and urine. That's what comes from our farms. So standard, and I'm talking about human feces and urine here, not animal. So standard treatment processes return the sludges to agriculture to a great extent, usually after composting. So a lot of work has been done on that. But there's quite a lot of treated effluent that leaves as a waste product, which goes to rivers or seas. And a certain amount of the sludges will go to landfill, toxic elements in particular. So there's a bit of a loop here. It's not the most efficient way to do the whole thing. And we're losing a certain amount of carbon as we do so. And we're using a lot of energy for that whole process. Now, if we can shift that, if we can get energy mainly from solar and from biofuels to go into our agriculture, relying on the sunshine to grow our plants, which happens at the moment anyway, biofuels as a source of biodiesel for powering machinery and the like, and simply use plants to fix our nitrogen and use animal slurries and the like, rather than relying on artificial nitrogen. So we've got the same, feces and urine. If we go for fecal separation units and urine diversion, then we can use the urine directly as a fertilizer back in agriculture, very safely, very effectively. And if we've got fecal separation, we can make fecal compost, human manure, and that in itself fixes atmospheric carbon dioxide. So basically, imagine it. You go to the toilet, you look in, the fertilizer is the yellow, and the solid bits are basically stored carbon that's been refined from the plants that have been grown. So that's a carbon sequestration cycle already in process. So if we can compost that and return it to agriculture, the carbon yields within that process are about twice as much as the carbon yields from composting sewage sludge. So there's a lot more carbon sequestration potential exists than we're currently utilizing in our agricultural systems. And then the flush water from that process can go into willow plantations for biomass generation. So that biomass can be used as an ethanol source, it can be used as a fuel source, and we've got that cycle of atmospheric carbon coming back in to be sequestered in the willows as well. So there's a closed loop there as well. So that's a much more closed loop system than is currently in place. And so these are some of the technologies that are used for source separation. This is a dry toilet unit. It's at a flamingo park in the south of France. And the reason why they had dry toilets there was because the waterways that they were close to were way too sensitive for any flush toilet system. So the most ecologically sensitive system was a compost toilet. And there's a lot of domestic scale systems that can be used as well. These are waterless urinals. Waterless urinals are common enough now as a water saving measure, but one of the big advantages of them is that you can divert the urine very easily and store it for export to agriculture. This is a Dublin toilet. It's a Norwegian model. And when you sit down, yeah, lads, you have to sit down, then the urine goes into the front section, and there's a very, very low flush volume that goes with that. And then the fecal material goes into the rear section as normal. So that flushes out the yellow water, and then the brown water at the back goes in another direction. Now, that's an easy way to recoup nitrogen from essentially fairly standard housing practice without anybody really knowing that the nutrients and the biomass are being recouped. And this is in a unit called an aquatron unit. It's a Swedish unit. The flush water comes in here from the toilet, swirls around inside in the vortex separator. There's a half tire unit here essentially that gathers that water and routes it off to the constructed wetland, and the solids then fall into the compost chamber underneath. So you have your fecal composting unit. You ram there's an iron bar that goes through there, and you crank it around a quarter turn every quarter of the year, and then you open up the chamber and take out your finished compost at the end. So they're just a number of the different source separation units that are available. And I'm going to do a shameless plug and say that the Reed Bed book and the Septic Tank Options book give a lot more overview of these. The Septic Tank Options was written as a more complete look at more natural systems, but also looking at the conventional systems as well. And the Reed Bed book then just looks at designing, building, and planting your own treatment wetland system, whether it's a constructed wetland or a gravel reed bed. And the others then are my attempt to circumvent the incineration policy in Ireland. If we don't have any waste, we won't have any incinerators. So it's a nice simple one. And anyway, in terms of circular economies, we basically need to move towards zero waste anyway, in order to climb out of our biodiversity emergency and climate emergencies. So that's pretty much the sewage treatment element in a nutshell. I'm going to look very briefly at SUDs and buffer zones. So you're familiar with SUDs, sustainable drainage systems or sustained urban drainage systems, and then buffer zones are the more agricultural type of filters. So in-channel ponds and wetlands, riparian buffers, that type of thing. I won't stay on this slide for long. I'll just say that I look briefly at stormwater ponds and swales are the two main ones in the SUDS types. And similarly in the buffer zone types, we'll be looking at swales and conventional buffer strips. So with buffer zones, I look at SUDS first. So for sustained urban drainage systems, for runoff that comes from paved surfaces, from hard surfaces, so say a new housing estate, for example, a number of things happen. The volume of overall water increases, the volume of runoff in a peak event increases, the pollution load increases, and the frequency, the storm intensity increases. So if we can simply stop our pipes at the earliest opportunity and have an open drain, this is the head of an open drain that flows on down towards a stormwater wetland. As soon as we get the water out of the pipes, it begins to settle. So that's a clue as to how we start to treat it. You know, we just make a system that's as big as possible while still affordable and not taking up too much land. And you can see the plants already here beginning to encroach from the edge. So that's a clue that we can do a lot with stormwater wetlands for treating water. This is a wetland just after I planted it on the Ruski bypass. And again, we've got a grass strip that will be at the edge of the motorway, and then the water goes into this planted wetland channel. And a stormwater pond in UL in the car park there. It filters the water coming off the car park, and that doubles for habitat as well. So, you know, they make very attractive wildlife ponds as well as everything else. So that's just a brief mention of SUDS units. In terms of buffer zones, this is the same basic idea as the Ruski bypass. It's the bottom of a farm in North Cork. We simply widened out the drain a bit, and we've got a box of plants there ready to go into the basin. And we'll plant it up, and that'll filter the water as it runs off the fields. Now, at the moment, that water doesn't need to be filtered, and yet we saw in the beginning of the talk how the water quality had declined for almost every stream in the country. It's these type of measures that can help to protect those streams. So even if there isn't noticeable pollution, these types of measures can help with farm drains. And for small drains, even tiny drains, like you can't even see the drain there running along the side of the road. And this was a community voluntary day where lads from the local community came out in North Cork. I think it was a leader-funded project. And basically I got them digging drains. So we're digging out small little ponds, building dams, jumping up on top of the dams just to hold the water into place, and then planting yellow flag iris in behind them. And you can see at the end of our day, even though there was no visible flow at the outset, you can see the water beginning to accumulate in behind each of the dams. So when there's stormwater runoff coming off the road, it'll gather there, it'll settle. All of the usual constructive mechanisms will become active as the plants and the microbes and the leaf litter and debris all begin to filter out the water. And in terms of flooding and droughts in the wider landscape, it also helps to modulate the hydrology of the landscape, slowing down the water, holding onto it, and bleeding it out nice and slowly during drier weather, and just helping to regulate the landscape flows. Of course, if you don't have the resources to pay for a couple of lads to come out and a box of plants, the other thing is to get some beavers. This is a photograph of the beaver dam. It's either a beaver dam or a beaver dam analogue, which is the man-made beaver dams that are used as well. Beavers do a fantastic job of dam building, obviously, and these can be excellent large landscape scale stormwater measures that are shown to hold on to the water, to flood the land upstream of them, flooding into the wooded areas during wet weather, but protecting towns and villages downstream. And your beavers are going to work for you for free, basically. So it's a very effective way to do it. But looking at the wider landscape, if you haven't heard of the wolves of Yellowstone, it's worth looking up George Monbiot's talk on the wolves of Yellowstone, because what they've found there is that over the years, since wolves were reintroduced into Yellowstone, the course of the rivers has basically changed because the large grazing animals are no longer able to get right down to the water and stay there for a long time, causing erosion of the banks. So they keep on the move all the time. So the aspen and willow are recovering and have stabilized the banks and protected them. So the wolf's job is basically to keep the grazers on the move. One way that farming can replicate that is to use holistic planned grazing and that type of thing, which keeps the animals on the go every day into different paddocks and helps to get the correct footfall and the correct grazing time. Now, the bison or large grazing animals in general help to open up the soil, help to create space for new wildflowers to come in and get their roots in and keep things open and dynamic. And then the wolf just keeps them on the move and keeps the footfall right. And the beaver, as we've seen, has its own role. So rewilding is something that I'm looking at more and more in recent years, partly because of the scale of the problems with biodiversity and with water quality and with carbon, actually, and climate. It seems to answer all of those questions. And there's obviously a lot of questions that need to be asked about how it's done and to what degree we do it. We can certainly do the work ourselves of some or all of these animals, but if we do, it's just an expensive process. So we can see here, I mentioned briefly, the bison create shallow margins in the landscape. They expose the soil. They also add nutrients and cycle nutrients. So the wolves protect the river, prevent overgrazing, and then they modulate the grazer footfall. And the beavers obviously slow the flow, make dams that filter the water, remove the shade, opening the water, and provide water storage as well. Humans can be net beneficial. So it's not that we're always detrimental by any means, but we have been called a desert-making species. What we seem to do best is make deserts. You know, whether it's the Sahara or the Australian outback or the Dust Bowl, that's what we've done in the past. And we're needing to shift our whole landscape management and our agricultural management so that we practice regenerative agriculture, regenerative farming. So we begin to either do the work of these animals or create the space for these animals to come in and do that work for free. So we're a very costly species substitute, but we're a hyper-keystone species, such as our impact on the landscape generally. This is a wetland rewilding project. In rewilding terms, it's very modest scale. It's 60 acres, just outside Limerick City. And you can see the toll booth there as you're driving north towards Galway from Cork under the river as you pass through the tunnel. And what I've done here is kept the shallows, the outer margins, as shallow as possible, so that any variation in water level rises and falls, leaving a wide shore, and that maximizes the habitat area. You can see the islands in the middle here. They've been designed in a star shape, so that whichever way the wind is coming from, the wading birds and waterfowl are protected from the wind. So this is part of a rewilding area rather than it was designed for habitat by the road company. Well, no, I did the design, but it was paid for by the road company when they were finishing off the works. It had been the old silt ponds, so when the tunnel sections were dropped into place, the silt from there was pumped into these stilling basins, and then reintroduced the cleaner water, then reintroduced back into the Shannon. So after that was done, we needed to return the area to ecological benefit, and that was the outcome of that. So that was our design drawings. I think it was the first road project in the country that used the permaculture principles. So these are David Holmgren's permaculture principles, and I don't think you can actually read the quality of it there, and I won't go into it, but just look it up. Look up David Holmgren permaculture principles, and it just provides a very, very effective framework with which to design any project and to look at any project. And let me see. Finally, there's a number of aspects to rewilding. One is the keystone species, which we've looked at briefly. One is core protected space, which Limerick is a modest example of that with the 60-acre wetland, but other rewilding projects have much larger core protected space. O.E. Wilson, the ecologist, suggested a half-earth policy, so half the earth for us and our farms and our landscapes and our materials, and half the earth for nature, as a way to practice very, very large-scale rewilding, specifically in order to let wildlife recover from the impacts of capitalism, I suppose, but human impacts more generally over the years. So the third element in rewilding is carnivores or keystone species, core protected space, and corridors. And I think there's a huge potential in Ireland for just linking up river corridors. If we were to put a 10-metre or 20-metre buffer zone on the perimeter of every stream and river in the country, very, very quickly we'd be using land that's already not the very, very highest quality agriculturally, and creating a web of corridors that wildlife could navigate through. So I think there's enormous potential there for reversing that trend of losing these very, very high quality, pristine reference quality rivers and streams through a combination of good sewage treatment, natural treatment systems to filter our sewage treatment systems to a very, very high standard, and then agricultural buffer zones and the like. And if we can combine that then with spaces for people to get back to nature and enjoy it, if you can imagine fields on either side of this area, just out of sight, with good dense buffer zones on either side, those corridors around the country could form not only a network of corridors for wildlife, but also places for people to get back into nature and to enjoy contact with the landscape. And that is it. I'll see if I can close this now. So there you are. That's a quick overview of constructed wetlands and reed beds, looking at the different types, looking at the other applications with willow systems and looking at dry toilet systems, source separation units, and then looking at SUDs and buffer zones, and then onto rewilding briefly. And they all tie in together very much. They're all part of the same general process of looking at how we manage our landscapes. And ideally, how we can build regenerative culture, whether that's in our sewage treatment to provide a source of fertilizers and a source of biomass, or whether we do it within our agricultural landscapes. So thank you very much for listening, and I hope you enjoyed it.